Example 8, graphing velocity and acceleration. A car starts from rest, and the graph of its position function is shown here on the left in figure 12. This is a position function of a car, where s is measured in feet, the distance, and t is in seconds. And what we want to do is we want to use it to graph the velocity, which is what we have on the right here, and the acceleration of the car. Once we do that, then we want to find out what is the acceleration at t is equal to 2 seconds. Okay, so first we want to do is we want to measure the slope of the graph of the position functions at the values of 0, 1, 2, 3, 4, and 5, using the method of example 1 that we've done at the very beginning of this section. And then we plot the graph of the velocity function v is equal to f prime of t. So let's go ahead and just take a look at here. So here we have 0, 1, 2, 3, 4, and then 5. Okay, now if I want to find here, I want to find the slope at the point 1. Okay, we already know that s or v prime of 0 is 0. So that gives us the ordered pair of 0, 0 on the velocity function. Okay, now if we take a look at the point 1 here, if we create a triangle at this triangle here, we can see that the height is going to be 13, and we have an approximation of 1. So we can see here that the velocity at 1 has a slope of 13. So our ordered pair is 1, 13. Then if we take a look at point 2, if we want to find an approximation of the slope, and again, you're approximating here. If you approximate this slope, we get approximately 23. So the velocity at 2 has an output or the slope of 23. So therefore, our ordered pair is 2, 23. Okay, and then at 3, if we create a tangent there, we want to find the slope of that tangent, we get approximately 31. So the slope is 31, so we get 331. And then at 4, if we want to find out what the slope is at point 4, then we get a slope of 35. Now again, these are all approximations. And then at 5, we can see that we get a slope of approximately 40. So the velocity at 5, we get an approximate slope of 40. So that gives us our ordered pairs. Now if we plot these, then we should be able to get the velocity function. So we have 0, 0. And then we have 1, and then approximately 13, 2, 3, 4, and then 5. And at 2, we have approximately 23. And then at 3, we have approximately 31. And then at 4, we have approximately 35. And then at 5, we have approximately 40. So therefore, this allows us to be able to plot the graph of the velocity function here. Okay, so now that we have the velocity function, now we want to be able to find out what is the acceleration at t is equal to 2 seconds. So what we want to do is the acceleration of when t is equal to 2 seconds is when a is equal to f double prime at 2. So the slope of the tangent line to be the graph of f prime when t is equal to 2, we can estimate the slope of this tangent line to be the following. So we're going to use our graph down here to do that. Okay, So if we take a look at the point 2 here, so this is 2, this is 3, 4, and then 5. Okay, now at the point of 2, okay, we know that we want to find the acceleration a of 2. And so what that equals is f double prime of 2, which means at the value of 2, okay, we create a tangent. Okay, and so that means we want to find the velocity at the value of 2. So when we create our slope triangle, okay, we can see that we get 27 over 3. So that means we get approximately 27 over 3, which equals 9 feet per second squared. Now, we also have to keep in mind of the units, because the units here we're talking about in acceleration are written as feet per second squared. And so now let's take a look at the acceleration graph. The acceleration graph, we have 0, 1, 2, 3, 4, and then 5. Okay, so we got to figure out what is the slope. So if we want to find the slope at point 0, we want to find the tangent at that line. Okay, so if we want to find that slope, okay, we end up getting an approximation of 15. So that means that the acceleration at 0 is going to give us a slope of 15 on the velocity graph, which tells us that we have the ordered pair 0, 15. Okay, and then at 1, we have an approximation of a slope at 12. So at 1, we have that in brown there, we have an approximation of 12. So again, those are approximations. We have 1 and then 12. And at 2, we found that to be 9 for the slope on the velocity. So we have 2 and then 9. And then at 3 on the velocity graph, the slope was approximately 7. And then at 4, we saw that on the velocity, the approximate slope is about 5. Now again, these are approximations, so that when you look at those slopes, again, they're approximations. And then here at 5, the slope on the velocity is approximately 4. So that is 5 and then 4. So if we look at our graph here on the acceleration, we have 0 and then 15. And then at 1, we have approximately 1 and then 12. Okay, at 2, we saw that that gave us around 2 and then 9. And then at 3, it was approximately 7. And at 4, we had approximately 5. And then at 5, we saw that the slope was approximately 4. So therefore, again, this just gives you an idea of how to graph these functions. So we can see that we have the position function. The derivative of the position function is the velocity function. And then the derivative of the velocity function is the acceleration function.